Hi everyone, today we're going to go over electrostatics. The last time you talked about electrostatics was probably in grade 9. This unit is called electricity and magnetism. So before we start talking about electrostatics today, I want to clarify a couple of things. Electricity and magnetism are different. It is very common for students to get them confused. Electricity involves charges. Charges can be positive or negative. Magnetism involves magnets. Magnets have north and south poles. So electrostatics and electricity, we're talking about charges. Magnetism, we're talking about magnets. Keep that in mind, don't get them confused, but today we're just going to focus on electrostatics. So first of all, what is a charge? It's kind of hard to describe, but basically you should think about charge as a property that's possessed by matter, and it allows matter to interact in different ways with electric and magnetic fields. Charges, of course, can be positive or negative. Atoms, as we know, are made up of subatomic particles, and the particles that we focus on in grade 11 are protons, electrons, and neutrons. In the nucleus of atoms, that's where you're going to find protons and neutrons. Protons are positively charged, neutrons are neutral, they have no charge. Electrons are negatively charged particles that exist outside the nucleus. They happen to be much less massive than protons and neutrons. When an atom has fewer electrons than protons, it's positively charged, and we call that a cation. When an atom has more electrons than protons, it's negatively charged, and we call that an anion. Atoms are locked in place when they exist in solids. However, some solids have the very interesting property of having loosely held electrons. Those electrons can actually flow freely within the solid. Think about a metal. Metals are good examples of conductors, and that's why they have electrons that can actually move freely in the solid. Materials that do not allow electrons to flow within them are called insulators. A good example would be wood or plastic. This is an overview of the law of electric charges. This is something you've known probably since you were a kid. Number 1, opposite charges will attract. Number 2, like charges will repel. And number 3, charged objects can attract neutral objects. There are a number of ways that charges can be transferred between objects. Obviously, every single object is made up of many, many, many charges. When an object is positively or negatively charged, what that means is that the object has either gained or lost electrons. How do those electrons become gained or lost? Well, you can charge them by friction, you can charge them by conduction, and if you want to temporarily charge an object, you can charge it by induction. If you charge something by friction, you're taking two objects, originally neutral typically, you're rubbing them together. These objects have to be made up of different materials if you want electrons to transfer from one to the other. The material that has the weaker hold on electrons will lose electrons. The material that has the stronger hold on electrons will gain electrons, becoming negatively charged. So afterwards, one object will become positively charged, one object will become negatively charged. How do we know which material has a stronger or weaker hold on electrons? We use something called the electrostatic series. So this is an experimentally determined list that tells us which common objects have a weak attraction to electrons or a strong attraction to electrons. So for example, if you were to rub a rubber balloon on your hair, rubber is further down on the list than hair, meaning it has a much stronger hold on electrons. So when you rub those two materials together, the rubber balloon will actually rip electrons from your hair, leaving your hair positively charged and the balloon negatively charged. Your hair will tend to stand on end because all of your strands of hair are now positively charged, and positive charges repel. I'm not going to demo that for you right now. Next, there's charging by induction. If you want to temporarily charge an object, you can bring a charged object close to another one, usually a neutral object, and the charges in the neutral object will actually separate because of the charged object that's nearby, creating a temporary charge on the surface. Lastly, we have charging by conduction. If you take a charged object and you touch it to another object, you're creating a path for charges to travel from one object to the other. In this example, you will permanently charge the object that you touch. For some great demos of charging by friction, induction, and conduction in action, please check out the YouTube playlist and watch the 3 videos by Camille Bruckmann, where she goes over some of the labs that you did in grade 9 involving these 3 methods of charging. Next up, how do we quantify charge? Do we actually count every single electron that travels from one object to the other? That's a really bad idea because that would take forever. There are so many electrons that are transferring every time something gets a charge. The unit of charge that we use is actually called a Coulomb, represented as capital C. And the variable for charge is Q. Sometimes you'll see this as upper or lower case, but it always means charge. In 1911, a scientist named Robert Millikan performed a famous experiment where he suspended tiny charged oil droplets between 2 electric plates. Since he knew the mass of the oil droplet and the voltage required to suspend them in between the plates, he actually figured out the charge on an electron, and therefore how many electrons were in a single unit of charge called a Coulomb. Here's what he found. He found that there were 6.25 times 10 to the 18 electrons in 1 Coulomb, which means that the magnitude of charge on one single electron is 1.602 times 10 to the minus 19 coulombs. And of course, that is a negative charge if we're talking about an electron. That number will come up quite a bit this unit. So the magnitude of charge on one electron is 1.602 times 10 to the minus 19 coulombs. It's actually called the elementary charge, and it's often denoted as lowercase e. So that's the charge on one electron when it's negative, but it's also the charge on one proton when it's positive. The charge on any object can be calculated as the number of deficit or surplus electrons. That means the number of electrons that have been added or removed from that object multiplied by the charge per electron. The formula that describes that is Q, the charge, equals N, the number of electrons that have been gained or lost, times E, the charge on every electron. For example, if we have an object and that object had 1.23 times 10 to the 24 more electrons than protons, what is its charge in coulombs? Well, we simply plug into this equation. The number of surplus electrons on this object is 1.23 times 10 to the 24, and the charge per electron is negative 1.602 times 10 to the minus 19. Meaning, the final charge on that object is just negative 1.97 times 10 to the 5 coulombs. So we know that like charges repel, unlike charges attract. Do they have to touch each other to exert this force? No. Just like gravity. The Earth exerts a force of gravity on the moon. They don't touch. So these are examples of forces that are non-contact forces. Sometimes it's helpful to draw what's called field lines around a charge to better determine what force another charge would feel if it were located in any position around it in space. Drawing field lines is actually really useful in physics. When we're drawing field lines, you have to imagine a 3-dimensional grid existing around, in this case, our charge. At every single point on our grid, we're going to imagine a little vector, a little force vector, that's pointing in the direction that a charge at that location would experience a force. All of those vectors together is telling us exactly what effect that one central charge has on its surroundings. Let's start by drawing some practiced gravitational field lines around the central mass, because we understand gravity. We've talked about that before. Let's pretend that we want to release a tiny little mass somewhere around our central mass. What force would be exerted on that tiny little mass? Well, as you got closer to the central mass, it would experience a larger magnitude force, but the force would always be directed towards the center of the central mass. So our field lines would look like this. They would be directed towards the central mass. Notice that where the field lines are closest, that represents where the force exerted on our tiny little test mass would be strongest. Where the field lines are more spread apart, that represents areas where the force would be smaller. Now let's do the same thing but with a charge. Let's pretend that we're going to release a tiny positive charge somewhere in the vicinity of this central positive charge. And let's ask ourselves, what is the magnitude and direction of force that that little test charge would experience? Using this simulation, I'm going to drop this tiny little positive test charge at different locations around our central positive charge. Notice how the magnitude of the force is smaller the further I get from that central charge. The magnitude is larger the closer I get. And it always points directly away. That makes sense based on the fact that like charges repel. So the electric field lines around a positive central charge end up pointing away in all directions. We can do the same thought experiment with the central negative charge. Using the same simulation as before, when I place a positive test charge in the vicinity of my central negative charge, now the force exerted on my test charge is always inward. The magnitude again gets larger the closer I get to that central test charge. This tells us that the electric field lines around a central negative charge point inward, which looks exactly the same as the gravitational field lines around a central mass. Finally, we can describe the force between any two charges, let's call them Q1 and Q2, based on the separation of those two charges using the following equation. This equation is actually called Coulomb's law. Here is the force, the electric force exerted on a charge. That's equal to the product of the two charges divided by the distance between them squared, multiplied by this special constant, which is called Coulomb's constant. The charges, by the way, are in units of coulombs. The separation between the two charges has to be in meters, don't forget that, and the force is in newtons. Coulomb's constant is this number, but it usually gets rounded to 9 times 10 to the 9, Newton meter squared per Coulomb squared. Based on that equation, what does it mean if we get a positive answer? Well, if we get a positive answer, it means we've multiplied two positive charges together or two negative charges together, meaning the charges are going to repel. If we get a negative answer, that means we're multiplying oppositely charged things together. That means the charges are going to attract. Let's say we have two ball bearings, and they have charges of 1.45 nanocoulombs and negative 3.56 nanocoulombs. Now, if you're trying to remember what nano means, it means 10 to the minus 9. So these are very tiny charged objects. This distance between them is 90 centimeters. What electrostatic force do they exert on each other? Is it attractive or repulsive? The last part of this question you can probably answer for yourself right now, which is a good idea when you're solving these problems. So the first thing to do is to write down the equation we need to use, which is simply Coulomb's law, and to summarize what we're given. Don't forget, the separation between the charges has to be in meters. Nano means 10 to the minus 9. When we substitute these values into our equation, we end up with negative 5.73 times 10 to the minus 8 newtons. So a very, very tiny force. The negative sign, remember, tells us that these two charges are attracting, which is exactly what we can infer if we know their opposite charges to begin with.